Welcome back. We're in Projectiles Unit, Worksheet 3, problem number 3. Paul Konerko hits a baseball in such a way that it leaves his bat traveling at 43.4 meters per second at an angle of 28 degrees above the horizontal. When hit, the baseball is 1.2 meters above the ground and 127 meters away from a 3.5 meter tall fence. A lot of information there. If this is a home run, by how much does the ball clear the top of the fence? If it hits the fence, how high above the ground does it hit the fence? Cool. Now, hopefully, we're just reading this question, you're recognizing, man, drawing a picture is going to be super helpful as things become more and more complex. It's like I knew this was coming, and I was trying to let you in on the ground floor of how to do this. Okay, so a bat kind of gets bigger on one end and smaller on the other. That's not so bad. And he's got arms holding onto that thing. It kind of looks like a golf swing, the way he's holding onto it. He's smiling. He's got a helmet on, and their helmets look like that. It looks like an old-timey leather helmet. I should take some art classes at some point. Probably. All right, you got little cleats on there. All right, so then he hits the ball, and that's what we really care about here. So ball, and that ball flies off at 28 degrees above the horizontal. So that's probably 45. Hold on a second, I gotta fix something here. So let me change that. 28 degrees is maybe something more like that. Not that it matters too much. We're just doing representative stuff here anyways. And we said it was the original velocity here, V naught, is 43.4 meters per second. I usually like to label those things right on there. As for me, it's easier to look back at a picture and go, oh yeah, I do know that value, as opposed to find that again in the text there. But you can do it either way that you like. So that angle right there is 28 degrees. And then my blue bits there, that's going to be 43.4 cosine of 28 degrees. And then 43.4 sine of 28 degrees. Cool. Just as we know. Now let me draw in the path. The path, is going to take some sort of parabola. Looks something like that. And then we also have this obstacle here. So we have this fence, and it's 127 meters away. And I don't know if I should draw the fence lower or higher. So I'm just going to draw a representative fence here, label it a fence, in case somebody looks at this and goes, what the heck was that? And then 127 meters, technically the fence has 0 width here. We're not worrying about how wide that thing is. 127 meters, did I get that right? Yep, 127 meters away from the ball. And you'll notice there's a difference between the ball and the person. Yeah. We're not worrying about all those nitty-gritty differences yet. And we actually won't in this class. Maybe a little bit in AP Physics, but that's usually more college level. When hit, the baseball is 1.2 meters above the ground, so we got 1.2 meters right there above the ground. And then the fence itself is 3.5 meters high. I'm going to do it on this side. Again, we're assuming that the fence has 0 actual width there. So I guess it should be a line. Maybe I'll just go change that to a line. It'll be less confusing. Sorry. I should have planned that out differently. That's all right. You're getting better at this. So am I. We're all in that together. All in this together. Yeah, I've never actually seen that, but all of my students years ago would sing that. And now it gets stuck in my head every time I say something like that. Terrible. It's like a virus. Okay. So yeah, do I have all the information? I'm looking back, I got looks like I got all that. So if this is a home run, by how much does it clear? So we're really looking for, and I'll go ahead and label this down, we're really looking for the delta y, like right here of the ball. So maybe I should label it like that, and go, if the ball is there, what's my delta y when it's like right there? So that's one way to think about it. Another way to think about it is at my delta y. So another way to, let me do that in a different color if it's a different way to think about it. So another way to think about it is, so this first way is at 127 meters, what's my delta y? And that would tell me if it cleared the fence or not, and I'd be able to subtract that and see by how much it cleared it or by how deficient it is for clearing it. Another way to think about it, which is equally good, is to go, hey, when my delta y is 3.5 meters, what's my delta x? And so here you're saying, okay, well, if 3.5 meters, if it's 3.5 meters above the ground at more than 127 meters, it cleared it. And if it's 3.5 meters like way under it, then it's not gonna, if it was 3.5 meters over here high, then it clearly isn't gonna clear it. So clearly isn't gonna clear it, that's a bad way to say it. Anyways, so you can think about it from either way, and both are equally correct. By how much does it clear if it hits the fence, how high above the fence? Okay, great. So that's all we're really looking for. So let's get into it. So I'm going to do my x dimensions over here. I'm going to do my y dimensions over here. I'm going to separate them, but off center a little bit as I normally do, as I usually have more calculations in the y. And we could do it either way. I'm going to go ahead and set my delta x to be 127, and then see where its vertical height is. Why am I going to do that? I don't know. I'm kind of guessing that you're probably going to do it that way. But I've seen it done many different ways by many different people. And again, there's no right or wrong way to do that. Those two ways are good ways to do that. The acceleration in the horizontal dimension is 0 because there's nothing pushing or pulling it in that dimension there. And so that simplifies that. And then we have delta x, which I know that is equal to my velocity. Again, that's in the x dimension, so I might even put v naught x there times however long it takes to get there. Okay, great. Well, I think about this and I go, yeah, this is 127, great. And I know this one is the 43.4 cosine of 28 degrees, so I'm making notes to myself. And these are mental notes, but I put them down for you. And so now I can actually just figure out how long it takes to get there. So let's go do that, because that'll be interesting. So we'll solve for time there, and we get delta x over v naught in the x dimension is equal to my time. Now, notice you're like, why did you do that? Why didn't you just put in those numbers right away? That's super easy. You can just do that in your head. Well, the reason is because this is going to get more complex, and so I'm trying to show you the good ways to do this. So that's 127 divided by 43. Don't forget to put in parentheses there when you're putting in that denominator. 43.4 cosine of 28 degrees. Make sure that you're in degrees for the mode of your calculator there. And I get 3.314. It's like pi, but not. So I go and store that as alpha t in my calculator, so I remember that that's the time, and I don't have to punch that in later. So that's the time to get there. Okay, great. But I didn't care about the time to get there. Oh, that's right. I cared about how high is that thing there. So, well, let's go over to the vertical dimension here, and I'll keep going in purple because this is nice. I like this. When I was growing up, purple was my favorite color. It's like this deep purple. It's pretty close to this purple. Anyways, we're looking for the delta y, so I don't know what that is. I know the acceleration. Great. That's negative 9.8. I know the time. Great. That's 3.314. And if you asked, hey, why did you write down 3 decimal places, not 2? No reason, really. I'm going to use all of them in the calculation anyways. What's my v naught? Remember, that's v naught in the y dimension in there as well. And I do know that that's 43.4 sine of 28 degrees. And then again, I know the time is 3.314. So I know all of these things on the right-hand side, so now I can just go and put them in. So am I going to rewrite them? No, I'm not going to rewrite them. You've done enough of these, and you can see it all right there. So let's go ahead and let's put all that in. So I got a half times negative 9.8 times my, notice that I stored my time value as t squared, so now I can just put in alpha t and then square it, and it makes it super efficient. And then I add that to my 43.4 sine of 28 degrees. Don't forget about little parentheses there, and then alpha t for the time there. And I get 13.71, Again, that's a little slightly rounded, but I have the whole value in my calculator, meters. Okay, great. So does it clear it? Yeah, it clears it when it's 3.5. Oh, I'm sorry. When it's 120, I was going to say it backwards. When it's 127 meters horizontally to the right in my picture, then the thing is 13.71 meters high. So this delta y in teal there, that delta y is 13. Oh gosh, I just recognized that I didn't do something. Oh man, that's my delta y. Ooh, ooh, ooh. You might have made this too, or maybe you're shouting in your head, "Oh, Mr. Wishway, Mr. Wishway." That's delta y. Yeah, let's keep going with that. Did you miss that? It didn't start at my 0 position. Check that out. It started at 1.2 meters high. And so what's my delta y? Delta y is y minus y naught. The ending position minus the beginning position is 13.71. So then where is it at? So I actually don't want my delta y over here. Actually, what I want over there, and really I was looking at like delta y, I guess, between the fence and that thing. Actually, I want the position over there. And if I get the ending position, I already know the beginning position. My beginning position was my 1.2 meters. And so now I'm going to go put that in. So minus the 1.2 meters there, my ending position, I don't know what that is in 13.71. So I just got to add the 1.2 meters to my 13.71. And now I get my ending position, my y position is 14.91 meters. So now I can go back over here on my graph, and this is 14.9. I was writing down the other one, 14.91 meters high. And so clearly it is going over the fence there. And what is the difference by how much it clears the fence? Well, there we're just doing the 14.91 meters minus the height of that fence there, 3.5 meters. And when we do that, we get 11.41 meters higher than the fence. So I add some like a qualifying statement to that. What does that mean? That's what that means. You should always be adding some sort of statement to your final answer there, especially in slightly more complex cases like this. So yes, home run. Chunk chunk. Maybe that's inside this little box here. And then like colon maybe, or semicolon, 11.41 meters higher than the fence. Cool, great. I think we answered everything. Let's go back up and see if we answered everything. By how much does it clear the top of the fence? Yes, it does. If it hits the fence, how high above the ground does it hit the fence? We do that same calculation, that subtraction there, and we figure out that if it hit the fence there. Okay, that's it. Have a beautiful day. See ya.